Hi, Lorenz, are you there?
Hi, yes, I'm here. Hi, good to see you.
Hi. So let's get you set as a co-host here.
Right, I think you just need to make my iPad co-host.
So you're going to do it on the iPad.
Yeah.
Okay.
All right. That seems to work.
Looks good.
Okay, good.
All right, welcome everybody. So this week, Lorenz Eberhardt will tell us about scattering equations in ADS. Okay, please go ahead.
Right, thank you very much. So indeed, I will tell you about some version of CHY formula that holds in anti-de Sitter space. And so this is based on a recent paper I wrote together with Shota Komatsu and Sebastian Misera. I think Sebastian is here in the audience as well, so you can also direct questions directly at him or at me. All right, so let's get started. And to start with, I would like to review some features of the flat space version of that of the CHY formula. So in general, that formula rewrites tree-level amplitudes of certain theories as a moduli space integral over the moduli space of Riemann spheres with n punctures. So the rough formula goes like that. So you have some set of momenta, k1 to kn, and the tree amplitude can be expressed as this moduli space integral. Then you have some integrands, which I call IL and IR, and they're theory dependent. So we will come to examples later. And then importantly, we have this delta function. And that delta function basically localizes the integral completely. So in computing that integral, you just need to solve these scattering equations. In the scattering equations, you see that they're algebraic in the positions on the worldsheet in Zi and Zj. So what you need to do is to just write down all these equations, and they will have n-3 factorial solutions. And you just sum the integrand over those n-3 factorial solutions. And I should also mention that since we're integrating over the moduli space of spheres, there's of course, as usual, an SL2C Möbius invariance. So in fact, I'm writing here n, I guess I should have written as well a product over I. So I have these delta functions for all the scattering equations. And out of those n, only n-3 are independent because 3 are just related by Möbius invariance. And similarly, to appropriately evaluate that integral, you should gauge fix 3 of the coordinates as usual. And finally, we have here this momentum conserving delta function, which, yeah, is just there. Okay, so let me also point out, which I wrote here, that the momentum conserving delta function you could understand as an interaction of plane waves on Minkowski space. So it's just this integral. That might not seem very deep, but it will be important when we consider the ADS version. Okay, so let's look at some of these integrands. And basically there are two sort of basic integrands you can consider. And one of them is the Park-Taylor factor, which I wrote here. So it's a sum over the symmetric group and modulo cyclic permutations. And what you need to do is you need to evaluate these color traces, and then you put in the denominator the Zi minus Ej, and you sum over all possible permutations. So whenever you include a Park-Taylor factor, either as IL or IR in the formula, you're adding some sort of gauge group, because here you have written the generators of gauge of your gauge group, and you're taking the traces. So just for future reference, since I will need it a lot, I will write Zij as Ci minus Cj. Okay, and the other important building block that one often meets is this Pfaffian. And so we can take this I to be a Pfaffian of a certain matrix. And that matrix we can write in this block form. And so this A matrix here contains all the momenta. So it's ki.kj over Zi minus Zj. Then we have this B matrix, and that contains polarization vectors. So whenever you use this I, the Pfaffian as an integrand, then you're adding basically 1 unit of spin to your theory. So let's say we have a vector particle, then we have this polarization here. And then we also need these off-diagonal terms, these C's, which are contractions of the polarizations and the momenta. Actually, this matrix has a null vector, and since it's antisymmetric, it actually has 2 of them. So if we would take just the Pfaffian, we would get 0. So what we actually need to do is to delete 2 rows and columns. So you take 2 rows and columns here, and you delete them out of the matrix, and you take the Pfaffian of the remaining matrix. And by including this prefactor, you can check that it's actually independent of which rows and columns you deleted. Okay, and then you can check that this seems to be a good candidate for a gauge amplitude, because, for instance, if you replace the k by an epsilon, that object would vanish, and you check gauge invariance. So then the basic logic is that you can combine, remember in the formula we needed both an IL and IR, and for both you can choose either of the two, either the Park-Taylor factor or the Pfaffian. If you take both to be a Park-Taylor factor, then you introduce 2 gauge groups basically. So what you will get is a scalar theory with 2 gauge groups, which is the biadjoint scalar. Maybe let me write down the Lagrangian for that theory just for reference. So we have a kinetic term, and so this is a scalar field, but it has 2 adjoint indices for both the gauge groups, which I write as alpha and alpha tilde, and then we have structure constants. So there's a cubic coupling. All right. Then if you just take one of the Park-Taylor factors and the other factor Pfaffian, you will get a spin 1 particle with 1 gauge group, and that turns out to be Yang-Mills theory. And finally, you can take 2 of the Pfaffians, then you will need 2 polarization vectors, and that gives you the Einstein gravity amplitudes. Okay, so that's the nice story that exists in flat space. And the natural question now is whether a similar formula could also possibly hold for different backgrounds.
The question.
Yes, please.
You were looking at the amplitudes of which particles, like in, for example, Yang-Mills theory?
Of the gluons.
Of the gluons, okay. And in the biadjoint scalar, it's just a scalar, right? Because
there's just a scalar, so yeah. Yeah, thanks for the question. So it's just a pure Yang-Mills theory. There's nothing else. Right. So yeah, we could ask whether similar formulas also hold true for different backgrounds. But let's maybe look back at our formula, the CHY formula, and we see immediately that a lot of the ingredients are actually very flat space specific. So of course we have this momentum conserving delta function, which is only there in flat space, but also the scattering equations themselves, they also involve the momenta. So you would also expect that if you go to a different space, then you should replace that with something else. And finally, these integrands, the IL and IR, they can also depend on the fact that it's flat space. And in particular, this Pfaffian here also, if you look at this AI, BIG, CI, J, then you see that this also involves the momenta. So that seems to be also a flat space thing. So if you want to go away from flat space, you better need to change those ingredients. And to make my life a bit easier, I will look at the just the Park-Taylor factor. So I will take both IL and IR to be Park-Taylor factor, and sorry about that. And so the theory I'm looking at is the biadjoint scalar. And actually, as a disclaimer, we do not understand at present how to generalize the story I will tell you to those other more interesting theories, the Yang-Mills theory and gravity. Okay, yeah, so as I said, we look at the biadjoint scalar. And the CHY formula can be actually derived from a string theory. And the relevant string theory is not the physical string as you know it, but it's the ambitwistor string. So the ambitwistor string is really a version of string theory that gives gauge theory amplitudes. And the plan is now to first give a very short review on the ambitwistor string in flat space, and then try to generalize it to anti-de Sitter space, which will give us CHY ADS version of the CHY formula. All right, so let's look how that went. And I will just focus on the bosonic ambitwistor string. It turns out that this is enough, but there is a supersymmetric version of it as well. All right, so let's start from the worldsheet action. The worldsheet action is actually deceptively simple. So it's just in first order form. So we have a momentum here, and we have the target space position, but these are two independent variables here. And similarly, you should also note that there is just a d bar. There's no d as in the physical string. So in particular, the p mu will need to be a 1-0 form on the worldsheet. So it will turn out to be purely holomorphic, and the x is a scalar. The equation of motion tells you immediately that both p and x are holomorphic fields. And then we also have the action for this current algebra piece that I don't need to specify. So basically, you need this, these bosons, the target space embedding, and then you need these two current algebras in the worldsheet as well, because you need to account for the two gauge groups, essentially. But I will not talk about the action of those, because they will just carry over to ADS in a straightforward way. All right, and then you have to perform various gaugings on this worldsheet to turn this into the ambitwistor string. And one gauging we have to do, as usual, is, okay, so let me turn this around. So to promote it to a string theory, we need to gauge the worldsheet diffeomorphisms. In this case, since we chose this holomorphic version of the worldsheet action, we just need to gauge the holomorphic part of the energy momentum tensor. However, so there's a trade-off. Since we haven't gauged T bar, basically, we need to gauge another holomorphic spin-2 field. And this action has, in fact, another symmetry. And that symmetry is that you can vary the X field here and send it into the P field. And that symmetry, if you gauge it, reduces the target space to the so-called ambitwistor space. And the corresponding spin-2 current is P mu, P mu. So that one is, it looks kind of the same, P mu and del X mu and P mu, but they're not the same. They're two independent. P mu and del X mu is, they are independent here. So because we have these two spin-2 fields we want to gauge, that leads to two sets of BC ghosts. So we have the usual BC ghosts, but also B tilde, C tilde ghosts that gauge the H field. And since we also gauge two of them, the critical central charge for the matter fields will actually be 2 times 26. So like very intuitively, we just took the right movers and took all right moving degrees of freedom and put them to the left moving side as well. And the kind of amazing thing for this ambitwistor string is that it has very few vertex operators. And again, you can intuitively understand that, because since we're not having any right movers, level matching basically fixes also the level of the left movers to be essentially 0. So it's not completely surprising that the only vertex operators that exist are basically the tachyons. And for the biadjoint scalar, they take the following form. So we need C and C tilde, because we have both this BC and B tilde, C tilde ghosts. Then we have the usual plane wave. And since we want our vertex operators to carry two adjoint indices of the two gauge groups, we include these two internal currents here that are denoted by K alpha and K alpha tilde. And for this, to satisfy the mass chain condition, we need that K is a massless momentum. So yes, so also you should recall that in the CHY formula, all the fields are massless, and that's very important for it to work.
Can I ask a question?
Yes, please.
Can you go up?
Yeah.
So this P partial bar X, that looks like a beta gamma system with lambda equals 1. Is that right?
Yes, yes.
So and this U1 symmetry is basically the ghost number symmetry, that beta gamma system, which is, I thought is anomalous, but you're gauging it here.
Sorry, I'm not gauging a U1 symmetry.
Sorry. You're gauging the delta X equals alpha P symmetry.
That's not the U1 symmetry, because this alpha is a holomorphic vector field for that to work, because X is a 0 form and P is a 1-0 form. So, and the corresponding current is spin 2, is this H.
Okay.
So the U1 symmetry you're talking about would be something like P mu X mu, right? That would be the U1 current.
Right, I see. Thanks.
All right. So let's take these vertex operators. Maybe let me keep them here, and let's compute the correlators. So let's try to compute some correlator like this. We have, and they have two indices. So I would compute something like that. So one bar, and then all the others. And okay, so let's try to compute that correlator. First, let's do the CFT part, which is that, and later we will need to do the moduli space integral as well. That comes from the gauging of T and H. Okay, so these K's and K tildes here, they're pretty straightforward because they're just decoupled degrees of freedom in the worldsheet. So these are just affine currents, and we just need to take the correlators. And it's actually quite an easy calculation that this they both precisely lead to this Park-Taylor factor. There's one subtlety here that I'm suppressing. You basically need to throw out, so if you take the correlator of these currents, there would be single sort of tree-level contractions where you only contract structure constants. But there can be, because there's a central term, there can be also double contractions, and I'm basically throwing them out. So that's something you have to do in flat space, and it's slightly ugly. But yeah, we can deal with it. And then you have the part of the correlator that comes from evaluating this correlator of the plane waves. And that leads to just the usual free boson correlator, and in particular leads also to this momentum conserving delta function. Okay, and finally, you might wonder where the localization on the scattering equations comes from. That's basically the only missing part in this calculation. And it comes from integrating out this constraint H equal to 0. So here we gauge two spin 2 currents. So what we actually would need, and they both generate gauge invariance. And for the T current, we need to integrate over the moduli space of Riemann surfaces. And for the H current, we need to, so to do it properly, you would need to integrate over the cotangent space of the moduli space of Riemann surfaces, because you're gauging both T and H. And you can actually reduce it back to the moduli space of Riemann surfaces. And to see how that goes, so you add a term in the action, which goes like that. So you have this P squared that you want to gauge. That's this H current. And in front of it, you have to write, so P was a 1-0 form. So P squared will transform as a 2-0 tensor. So that means that mu has to be a Beltrami differential for that thing to be a 1-1 form. So you add this term in the action for the gauging. but now you have to integrate out your Lagrange multiplier, the split Riemann differential. And so if you do the path integral, you will actually get a term like that. And already now you see if you naively integrate that out, mu is just linear, so you can do it. And this p is pinned to a particular value in the theory. It's a free theory, so I can just put in what is the value of p. And one easy way to determine it is that you see you can derive that p has the following OPE with these plane waves. It's just the usual OPE that you get. Here you get k mu back, z minus w. So that means that you know all the residues of p here, and that fixes on the sphere p fully to have that form. So what that now essentially says is that since you gauge p squared, you need this p squared to vanish, and the double poles of p squared vanish automatically because k is massless, and so you just need to make sure that all the residues of p squared vanish. And the residue of p squared give you precisely these scattering equations, which for reference were this 2ki.kj over zi minus zj. So that's basically how this delta function of the scattering equations come about in this modular space integral. All right. Are there any questions to this? Maybe it's a good time to take questions. Okay. So basically now I want to repeat the exact same story by promoting the target space from flat space to ADSD plus 1. And I will do it in 2 steps. I will first take the target space to be the group manifold SOD, 2, and later I will gauge out the subgroup SOD, 1 to reduce it back to ADSD plus 1. So let's see first how the worldsheet action would look like if we take it to the target space to be group manifold. And it's basically what you, if you think about it, what you think it should be. Namely, you introduce some trace on the Lie algebra of your group. And you make P, before we had P mu, so it was valued in the target space, a 1-0 form that was valued in the target space, and now it's valued in the Lie algebra. And similarly, you have, instead of X, you introduce a group valued field G, and then the kinetic term just takes the standard form G to minus 1 del bar G. And I also introduced this parameter H bar. That parameter H bar is actually redundant because I could just rescale P and get rid of it in my action. But I will find it convenient to keep track of quantum corrections in the model. Okay, so this simple action, and what I should also have written is, of course, there's also this current part. That's just the same as in flat space.
I have a question here.
Yes.
So can I think about the worldsheet theory as some curved beta gamma system? What I meant is that the beta gamma system can be defined on a general target space. Well, actually that's part of, so classically one can define the beta gamma system on a general target space, but then there's a quantum anomaly.
Yes, I think, I mean, it would be for sure very similar. I'm not sure whether it's exactly the same, but there will be an anomaly, you will see. So okay. I would say yes, but I'm not familiar enough with the curved beta gamma system.
So for the usual curved beta gamma system, one condition for the vanishing of the anomaly is that the first punctured Young class of the target space has to vanish. So I'm just wondering, is that true for the group manifold you choose here and maybe the subsequent target space you are going to consider?
Yes, I mean, from a cohomological point of view, that's true, I think, because that SOD, 2 has the cohomology of a product of spheres, of odd dimensional spheres. So I think there's no fourth cohomology to start with. but the condition will be that you need to zero the dual Coxeter number. So it's not a topological condition for me, but yeah, so I will need to check.
Okay, thank you.
But yeah, thank you for the comment. Okay, so yeah, so this model has just has a left multiplication, right multiplication symmetry that is just the induced symmetry from the Lie group. So you multiply your group valued field by G left and G right, and that G left and G right itself can be a holomorphic function. And similarly, P is just multiplied by, conjugated by GR. And you get a left current and a right current, but they're both left moving. Just so J left is just GP G-1 and GR is just P itself. And now the idea is that to reduce it to ADSD plus 1, you should write ADSD plus 1 as a coset space. And so you want to gauge out a subgroup of either G left or G right. And let me choose here G right. So yeah, so I want to gauge the subgroup H, which is SOD, 1 inside GR. And so the strategy is now simply to add to the BRC operator that is present in the ambitwistor string to add also this subgroup gauging. All right, so we want to gauge T, and the energy momentum tensor turns out to be this part. And then if you require that the current, the two currents, so P as well as G left, should be primary fields on the worldsheet, then you will need to add actually this quantum corrections to the energy momentum tensor. So that's sort of similar as what you know from the Sugawara construction, where there's also quantum correction coming from the dual Coxeter number. And similarly, we want to gauge out H, which is still trace of P squared. And finally, we want to gauge the right moving current, but we only want to gauge so I put this index I, and I here runs only over the subgroup that we want to gauge. Okay, so now comes the disclaimer that what I'm doing here is actually slightly illegal, or it's very illegal if you want. So this gauging is anomalous. And you can easily see one place of anomaly that comes. For instance, H is actually a Suga, so P satisfies some Kac-Moody algebra on the worldsheet. And so H is the corresponding energy momentum tensor. And while the algebra is at level 0, there's still this H. So in the usual ambitwistor string, you need that H with H goes to 0. But that's no longer true in the OPE H with H. In this case, you get something like, I mean, you get terms back which are proportional to H. So the gauge algebra is no longer the same as in the flat space. The good news is that at least it closes, but the bad news is that it's anomalous. And for the anomaly to fully cancel, you need a lot of conditions. So the easiest condition to satisfy here is that the matter central charge is still 52. So that's the same as in flat space. And you can easily satisfy it by choosing an appropriate appropriate current algebra. However, you also need that the dual Coxeter number is 0. And that basically, if the dual Coxeter number is 0, then first of all, this quantum correction goes away here. But also this H will again go to 0, and you get the same gauge algebra as in flat space. And finally, we wanted to gauge also these currents, these subgroup currents, and that will be also anomalous unless we also satisfy the condition that the dual Coxeter number of H is 0. All right, so that's all not the case. So because our group G was just SOD, 2, so the dual Coxeter number is D, and the one of H is D minus 1. So that's essentially the reason why I included this H bar, because I want to continue nonetheless and basically throw away all the quantum corrections that I get from H bar. So that is slightly illegal, but it will turn out to still give the right formula, and we will prove the formula by different means. And here's also a good point to shout out that there's a paper by David Skinner and Kai Röhrig that appeared on the same day as our paper. And they analyzed the same ambitwistor string for ADS3 cross S3. And they do a superversion of that ambitwistor string. And that superversion you can actually make non-anomalous. So in their model, that is much better defined. You can look and they find essentially the same formula, but tailored for ADS3. And you don't need to do this coset story. Okay, so let's go on and let's write down the vertex operators. And the vertex operators, some pieces should look familiar. So we have this ghost part from the C and C tilde ghost. Then we have again these internal currents from the current algebra. And finally, we have a piece that replaces the plane wave. So before here, we had just this e to the ikx in flat space. Okay, so what is that piece? The field that I called x here is just a particular combination of this group value field g here. And so it's g acting on some vector q. And q is defined to be the vector that such that h is the stabilizer of q. So h is SOD,1 and g was SOD,2. So there's precisely one vector that is fixed by that subgroup. So, and I call that vector q and normalize it such that q squared is -1. So x is also now a vector, but it's really a field on the worldsheet still. And okay, so basically we need to look at that combination because we want this vertex operator to be invariant on the right multiplication, on the right multiplication of the subgroup, because we gauge that. So that's why only this combination appears. And then we need another vector with which we can contract x. So let me call that other vector p. So basically that motivates why here p dot x is appearing. And so the vertex operator should be some function of that p dot x. And by requiring that it actually satisfies all the on-shell conditions, you see that this function necessarily has to be p dot x to the -d up to some overall constant. And you also need that p is lifelike. So p squared has to be 0. And also, since this is homogeneous in P, this vertex operator doesn't really depend on the scale of P. So you could rescale P and still get the same vertex operator. And that is exactly what you would, what we identify with the bulk to boundary propagator in ADS in the embedding space formalism. And here P is now interpreted as the boundary coordinate of the vertex operator and X as the bulk coordinate. So basically, instead of K that we had in flat space, we're working here in the position space of the boundary, and we replace K with P. Okay, and finally, maybe I should also say that the conformal weight, the scaling dimension is fixed to be the dimension, such that since these are scalars, the Casimir is something like delta times delta minus d, which in this case is 0. And that's the analog of the particles being massless in flat space. Okay, so now we have the vertex operators. So let's go on to compute their correlators. And essentially the part that was present in flat space is exactly the same. So C and C tilde just give you some Jacobian from the gauge fixing, and the K and K tilde lead to these two-part Taylor factors. And finally, we have to compute the correlator of these bulk to boundary correlators. So let's write that in a path integral version. So we would need to integrate over all the G's, since they only depend on G. The on-shell action is 0, so that's why I didn't put it. And then we get these bulk to boundary propagators. And now we can apply essentially the same trick as we did before. We can fix actually G to be, G doesn't have any, the OP of G with G is trivial on the worldsheet. So that means that we don't have to integrate, we only have to integrate over G's here that don't have any singularities. Because if G collides with any of those vertex operators, there's no singularity. And G is also a group valued function on the worldsheet. And the only way that these two facts are compatible is that G is just a constant. So instead of integrating over all functions of G, this integral collapses to just an integral over S of D, 2. And then it further collapses because that the integrand actually does not depend on G itself, but it only depends on that X. And remember that X was this G acting on Q. And so it further collapses to an integral over just ADSD plus 1. And since the integrand is invariant in the right multiplication and transforms covariantly in the left multiplication, the measure of that integral is also fully fixed to be the unique invariant measure on ADSD plus 1. So what we get in the end is just an integral over ADSD plus 1 of these boundary propagators, which is nothing else than the scalar contact Witten diagram. So that should ring maybe a bell, because before we had this e to the, in flat space, we have this correlator, and that led to the delta function of the momenta. And and I told you in the beginning that we should think of that delta function as n-plane waves that interact in Minkowski space. And so now what replaces it is this scalar contact Witten diagram. Okay. And the other important part of the formula of the CHY formula was this localization part on the scattering equations. So, and the way we saw it before is by integrating out this Beltrami differential that acted as a Lagrange multiplier of this spin 2 field, this trace p squared that we want to gauge. And as before, p is pinned to a particular value, and that particular value you can write as so. However, it's a bit more subtle than before. So what appears here instead of the momenta are the conformal generators. That in embedding space you can just write like that, p alpha. Yeah, that's just a combination. And so you should understand that as being, that's the value what p takes, but acting on the correlator here. So p is still operator valued in that equation. And but now the same argument as before tells you that there should be localization on all the values where the residue of p squared is 0. And the residue of p squared gives you now the analog of the scattering equations. And you can write them again in the same form. And formally, you just replaced the momenta ki, but by the conformal generators di. And that finally leads to the ADS version of the CHY formula, namely that you can express a correlator of n of these biadjoint scalar fields as a modular space integral over the punctured Riemann surfaces, Riemann spheres. You get the scattering equations here. You get, as before, these Park-Taylor factors, and instead of the momentum conservation, you now get the scalar Witten diagram. So again, there's a useful way of remembering this. You just replace the contact diagram in flat space with the contact diagram in ADS, and everywhere you see a ki, you replace it with the conformal generator di. Okay. But there is, of course, a very novel feature, namely that the scattering equations are operator valued. So you might complain that this formula is kind of a stupid formula because we have a delta function of an operator. So how are we even supposed to evaluate that formula? Okay, so let me first explain how you should understand that formula and then prove that formula. Okay, so as a first comment is that the good news is that at least all the scattering equations commute, which is not obvious from the formula. And that means that you can find a simultaneous eigenbasis to all the scattering equations. So for instance, at 4 points, we just have one scattering equations because by Möbius invariance, 3 are redundant. So let's just pick the second one. And written out, it has this form. And just factoring out some factors, you get this formula. And this is actually kind of nice, this formula, because it tells you that the scattering equations, they interpolate basically between the conformal, between the Casimir of the S channel, T channel, and U channel. So in writing this, I wrote d1.d2, I wrote as d1 plus d2 squared, because I will use frequently that the Casimir of the contact diagram is 0. So that means that, yeah, so this one acts on the contact diagram, so I can just put d1 squared to 0 there. And now let's say if z3 is z2, then we would kill this term and we would kill this term because there's z2, 3. So if z3 is z2, then we just keep this term and we get the Casimir of the T channel. And similarly for specifying z3 to z1 or z4, you get the S and T channel. So in particular, that means that the eigenfunctions of these scattering equations are some objects that interpolate between the S, T, and U channel conformal blocks. So that's why we called them in our paper generalized conformal blocks. And you can at least, while we do not know them explicitly, we can find some nice relation of these to an integrable model. So the conformal blocks in general are related to the Calogero-Sutherland model. And in this case, if you add this z parameter, this z2 parameter, turns out that the eigenfunctions are given by the eigenfunctions of an elliptic deformation of the Calogero-Sutherland model, which is the so-called Inot-Semtsev model. Okay, so that's nice, but how does it tell us how to evaluate the formula? And so basically what that means is that you take your contact diagram, you should decompose it into these eigenfunctions that here I called C lambda with some coefficient A lambda. And now, of course, you can make sense of this delta function of the scattering equation acting on this contact diagram, because in the eigenbasis you can define it. And then you would need to pull out that the sum over the eigenvalues, you would need to pull out of the integral, and then you can just evaluate the integral as usual. Okay, admittedly, that sounds very complicated, and we have not succeeded in pulling in finishing that calculation, because you would need to show that these eigenfunctions form a complete basis and so on to really make that work and to define some norm. So instead of doing that, what I will do is to just evaluate the formula by contour deformation, and that will also give a proof of the formula. Okay, but admittedly at this point, it's not a computational advantage unless you understand really how these eigenfunctions look like. Okay, so are there any questions so far?
I have a question.
Yes, please.
Can you say more about the significance of the connection to this integrable model? Like what could you in principle do with this connection?
I think it's just useful because, I mean, people have already studied this model, so you know that these eigenfunctions exist. And I mean, yeah, maybe another nice thing is that basically, so you might ask, why is it an elliptic deformation? And basically that comes about because you have to go to the pillow coordinates of this 4-point function to see it. And then basically the pillow coordinate gives you the elliptic parameter in that deformation. But yeah, it's not super useful for something right now.
Thanks.
Yeah, but I find it kind of fascinating that this is some object that interpolates between the 3 channels. So I'm not sure whether it will be useful for.
Yeah, I agree. That seems really interesting.
Yeah.
Yeah, thank you.
Right. Okay, so as I said, let's just evaluate the CHY formula using contour deformation. And let me just focus on 4 points, although you can do that at any points. And the idea is to write this delta function here as an antiholomorphic derivative of 1 over z. And by doing that, you basically transform the two-dimensional integral over the moduli space into just a contour integral. So we just need to evaluate these holomorphic contour integrals. And so in the case of the 4-point function, what the formula amounts to is you get this correlator of 4 points, and the argument of the delta function goes in the denominator. So you have now 1 over the scattering equations there, and then you get this Jacobian from gauge fixing. So I fix Z1 and Z3 and Z4 and keep Z2 as variable. And then as usual, we have the Park-Taylor factors and the contact diagram. Now you might ask, where should the contour run? Before we had an integral over the full plane. And basically because of that delta function, it should run, so whenever you have a delta function here of some, let's say the scattering equations, and you run over some disk where there's this scattering equation becomes 0. Now you replace that with this, the bar of 1 over scattering equations over the disk. And now you use Stokes' theorem to rewrite this as a contour integral over the boundary of that disk. So that means that this contour gamma that appears here should encircle all the poles that come from the scattering equations. So that integral has some poles that rise because that scattering equation hits the contact diagram. And then it also has other poles that come from these Park-Taylor factors, and we're not integrating around those. Okay, to simplify our life a bit further, we can color order the correlators, like we do in Mills theory. And since we have 2 gauge groups, we can actually doubly color order them. And what that amounts to means is just that we pick a specific permutation in the Park-Taylor factor. So recall that the Park-Taylor factor was a sum of all the permutations, and now we're just fixing one term in the sum. And for simplicity, let me just take the identity for both the left and the right movers. But this story, what I'm going to tell you, works independently of what you choose. So now I want to compute this color-ordered correlator where both the permutations are the identity. And I can write it now like this. So I get some zij's, some come from this gauge fixing, some come from the scattering equation, and some come from the Park-Taylor factors. And I rewrote my scattering equations as above, so that it's, again, looks like the sum of 3 STU channel Casimirs with some z's in front. All right, so the reason I did this is because now we know exactly which poles come from the scattering equations and which poles come from these prefactors. So there are poles in the prefactor for Z2 equal to Z1 and for Z2 equal to Z3. And then there are some other poles where we don't even know how many there are, what locations they have, and so on. So it's a priori quite difficult because you would need to solve this operator valued equation. Okay, but now it's nice that we can do complex analysis and we can just deform the contour gamma such that instead of enclosing all the poles that come from the scattering equations, it encloses all the other singularities, which means that Z2 is Z1 or Z3. Okay, so if we do this, then we can re-express our correlator as the sum of 2 contour integrals. And now it's very easy to just compute the residues of this integrand. And what we end up with is this. So we get the contact diagram, and we act on it with this 1 over the intermediate Casimirs. And from this point on, it's pretty straightforward to see that this is the same thing as doing Witten diagrams. Because first of all, these, they were derivatives with respect to the boundary coordinate. To connect to Witten diagrams, we want derivatives with respect to the bulk coordinate. So what you notice is that the bulk to boundary propagator is invariant if you rotate both the P and X. So that allows you to rewrite these conformal generators in P as conformal generators in X. And now whenever you have some term like sum of some d's squared that hits these bulk-to-boundary propagators, as they do in the contact diagram, then you can always convert it into this dx.dx, and dx.dx is up to a factor, nothing else than the ADS-D plus 1 Laplacian. Okay, so with that knowledge, you can finish the calculation. So the color-ordered correlator is this combination acting on the contact diagram, and using this identity, you can just rewrite this as 1 over Laplacian acting on 2 of these 4 terms in here. So it just becomes the sum of 2 terms with these 1 over Laplacians here. And the 1 over Laplacian, of course, is nothing else than the bulk-to-bulk propagator. And so what you end up with is these, the sum of these 2 Witten diagrams. And that is correct because these are the only 2 Witten diagrams that respect the color ordering. The third Witten diagram, the U channel, you need to cross, and it's no longer color ordered. And you can actually do the same calculation for any number of points. So you just need to be slightly or very careful with the systematics, and you have to deal with higher dimensional contour integrals. So for 4 points, it's very easy because you can just use the usual residue theorem. But for higher points, you have to use the global residue theorem from multidimensional complex analysis. But all of that analysis follows very closely to what Dolan and Goddard have done. They have proved first this formula for the biadjoint scalar in flat space with this method. Right, so I think I'm almost at the end. So let me finally conclude. So what we have done is to propose a generalization of the CHY formula to ADS. And so maybe let's write the formula one last time to recall it. So we want to integrate over the modular space of punctured spheres. Then we get the scattering equations, which take this operator valued form. And then we have these integrands, IL, IR, and finally we have the contact diagram. Okay, so far, as I said, this only works for the biadjoint scalar. And the main challenge to extend that to more interesting theories like gauging gravity, sorry, was there a question? Is to make sense of these IL and IR. So what we tried for a long time is just to do the naive thing and take the Pfaffian and replace all the KIs by DIs. But you always run into problems that the DIs are the conformal generators, they don't commute. So you end up with some matrix with non-commuting entries. And so in the Pfaffian, you don't know in which order you should write these terms, and that actually matters. So until now, we haven't found a proposal. And you might also argue, and I would agree, that this formula so far is not computationally useful. It might be useful for formal purposes to prove some properties of these correlators. But for evaluating these correlators, basically the only way I know is to do this contour deformation argument that reduces the correlator back to the Witten diagram. Okay, and finally, let me also make the comment that in principle, nothing was extremely specific here for ADS. So most should work for arbitrary coset backgrounds. So all this ambitwistor story, I just needed 2 groups and divide them by each other. So at this level, yeah, nothing can go wrong, I think, if you do it for different coset backgrounds. All right, so I think that's it from my side. Thank you.
Thanks very much, Lorenz. Are there questions?
Yes, I have a question. Thanks for the very nice talk. So it seems that here the mass of the particles in ADS, they are always 0. So is it possible also to extend this formula to other masses?
Yeah, so it's not really even known how to do this in flat space. The problem is that all this, I mean, the formula is not consistent if you just naively put in massive particles. So there are some proposals of how to fix this. So one easy idea, for instance, is to start with one dimension higher and do some sort of KK reduction of the formula. But as far as I know, nothing of that really works. So I'm also somewhat hesitant that something like that will work in ADS. Yeah, but I don't have a counter argument.
Thanks.
Although maybe one thing I can say with the KK reduction is that you can, for instance, put some internal group manifold. So I think you can do, for instance, if you start with some supergroup, you could conceivably do something like ADS 5 cross S5. And then, of course, from the KK reduction, you get some massive fields in ADS.
I see. Thanks.
Yeah.
I would like to ask a question, but it's based on my ignorance, so I'm not sure how to formulate it correctly. People discuss a string in ADS which is dual to when they were trying to calculate anomalous dimensions in Young-Mills theory, and this string in ADS also happens to be integrable. Is there any concrete relation between the integrable dynamics you see and what they discussed there?
So, I mean, the most obvious problem that we face right now is that our string theory is not consistent, because that gauging that we did on the worldsheet is not consistent. It's not something that you should take too seriously. There are ways to make the anomaly disappear, but so for instance, for ADS3 cross S3, you could take a supergroup, you could take PSE1,1/2, which has a vanishing dual Coxeter number, and then you could get a consistent theory. But in general, I don't know how to do this. And in particular for ADS5 cross S5, you need to put Riemann background. So that is not present in that model. So I think right now there's no connection of that sort because we just don't have a consistent model. And I would also not try to compute some loop amplitudes or something of the sort with this theory, because for sure we will run into problems. Yeah, so yeah, but I'm sure that one can do somehow better than what we did. So for instance, David and Kai, they did certainly better with their model in ADS3 cross S3. But it would be very interesting to lift this to ADS5 cross S5. So.
I have a pretty general question. So there are various other formulas for calculating scattering amplitudes in clever ways that go by various acronyms. Do you know what is sort of the status of the landscape of scattering formulas in ADS? Are there other ones that work very nicely, or is it, or no?
I mean, there's of course a huge bag of tricks how to simplify, how to make simplified calculations by not just doing the stupid Witten diagram calculation. And for some, I mean, some work very nicely. I think probably Shinan has some very nice closed form formulas recently for the supersymmetric backgrounds.
Yeah, I guess I had in mind the other ones that work in flat space.
Like, you mean something like BCFW relation regressions? Yeah. I think maybe if Sebastian is here, he can correct me. But as far as I know, there's no analog of that in ADS.
There is a paper by Subrat Raju, about something like that. Yeah, he has some way of applying BCFW type recursion relations, but it's a bit different than what you're doing. In particular, I think he breaks the conformal symmetry to write down the recursion relations.
Oh, that's okay. Thanks. Yeah, I will have a look. Yeah, but in general, I think many of the flat space constructions seem to break down. I mean, I'm also not yet convinced that the Young-Mills and but this is just a fluke maybe, and it just works for the biadjoint scalar, then it would be not very interesting. I think it just becomes interesting if we go to realistic theories. Yeah, maybe I should also. Sorry, please.
Go ahead.
I should maybe also mention that in flat space, there's all kinds of extensions to supersymmetric theories and so on. So you can, there's a version for almost every supersymmetry you can wish for. So yeah, maybe that also exists for ideas. I don't know.
I wanted to ask about the sort of the philosophy of these CH wave formulas in the ambitwistor string. So just even in flat space, how do we know when a theory should admit an ambitwistor string formulation, or when should we expect that such a formulation should exist? And similarly with CHY formulas, or do people know the answer to that, or is it mostly still just exploration?
I think it's just guessing. It's a big guessing game. So the table that I've shown you in the beginning is considerably bigger by that. So I mean, I've shown you the very basic table, the 2x2 table here. So there are at least 2 or 3 more rows and columns that are known. But there's no general, it's not like you give me a theory and I give you the CHY formula. That I think there's no understanding like that. That would be great, but yeah.
And does the fact, if a theory has an ambitwistor string formulation, does that mean that it has some particularly nice UV behavior or something?
Not necessarily, because so you can compute loop corrections in this in the ambitwistor string, but sooner or later that will need to, I mean, it's supposed to be equivalent to the field theory. So it doesn't mean that, so for instance, Yang-Mills has a ambitwistor description. It doesn't mean that it's particularly nice, the UV. It doesn't have a UV completion, or gravity also doesn't have UV completion. So.
So what are the stringy, is there some stringy aspect of these theories that one can see?
No, I think it's really a bit misleading to, maybe it's misleading to say ambitwistor string. I mean, in the end, this is a field theory. It's just constructed from a worldsheet point of view. Yeah, there's nothing stringy about these theories. Yeah, maybe one kind of stringy thing is that most of these theories that are known to have a CHY formula arise from some deep brain actions. For instance, DBI or something like that. But,
thanks.
Are there any further questions? Okay, if not, let's thank Lorenz for the nice talk.
Thank you.
Thank you.
Right, I will stay around a bit